Hello, my name is Daryl Hill. I'm the instructor for Comp 1805 Discrete Structures 1, offered in the summer of 2020. This is an alternate structured course. Of course, if you're listening to this video, you should know all about that. You should have done the reading from the course outline. And so today's lecture is going to be an introduction to discrete math. These slides are based off the slides of Dr. Robert Collier. So any mistakes you find are mine because they've been modified, and all the things that I've done properly and correctly are likely the result of Dr. Robert Collier. But yeah, so today we're going to talk a little bit about discrete math and why we learn discrete math and how it applies to computer science. And we're going to look at a few examples of how we apply discrete math to computer science to solve problems. Okay. So yeah, discrete math, what, why, how. So what is discrete math? We'll talk a little bit about what that means. What's the difference between discrete math and, say, regular math, or what is special about discrete math? Why does it matter to computer science? We're going to see that, computers are machines that work on discrete data. So we'll talk about what discrete data is and why computers are these machines that operate on it. And how do we apply discrete math to computer science? That is, how do we solve problems using computers and using discrete math. So what is discrete math? It's math for discrete data. So that's another question that comes up, is what is discrete data? So it's data that must have a definite value. So this is, all kind of vague. So let's look at an example. So imagine a set of coordinates in a plane somewhere. So from 0 to 4, we have these coordinates 0, 1, 2, 3, 4, and then we can put points inside the we can put points on the plane, and then we can identify where the points are by their coordinates. But while each point has a definite location, it's difficult to describe in this case, because this one might be at 1 point something, and in the x-axis, and at 0.9 something or other in the y-axis. But it's difficult to pin down the location precisely. This is in general, in the real world, right? So I'm not going to get into the physics of the whole thing, but yeah, so we have yet to find a precise location for a point. So we might describe it something like this, but at some point, if we're going to represent these using numbers that we can store in a computer, we're going to have to cut off the precision somewhere. So now we can imagine the same plane and imagine grid lines on it. And now we take each of these points and we assign it a definite coordinate based on these grid lines. So each of these points must be at the intersection of two grid lines. So now they take on exact coordinates. Some of the precision is lost. So when we solve problems with computers, often, we're solving a model of the problem, a discrete model of the problem, and so the values that we get back are not going to be, precise in every case, but if it's a good model, it will give us back something useful. So why discrete math? Why do we use it on computers? Computers are discrete machines that operate on discrete data. So if you know anything about computers, they're made up of bits. So that's so each of these little bits or switches is either on or off. It's a 0 or 1, or you can think of it as true or false. So that's what we mean. So this is binary data, and by binary we mean that each bit of information can take on one of two values. But whatever the data is in our computer, it's always well defined. We always know precisely the state of the data. We can always query memory and find out exactly what data is there. It's never like it might be a 0, it might be a 1. If that ever happens, then the computer recognizes that memory as corrupt, and it's unusable in that case. So computers are machines that operate on discrete data, and discrete math helps us to better understand discrete data. So using discrete math, we can say, using a computer, what problems can we solve? Because if you can solve it using discrete math, chances are you can solve it using a computer. How do we solve them? So what steps do we take in order to solve these problems? And what resources in terms of time and memory are required to solve them? So time and memory are very important in computer science because there are problems that we can solve but take too long, and there are problems that realistically don't fit into memory, and if our memory requirements are too big, then you have to go to disk, and that slows things down as well. All right, so we have so we want discrete problems, so we want to specify our problem in a very precise, discrete way. So we might some problems are very easy to model discretely. In fact, some problems are discrete problems, so it's not a problem. Some of them, though, we're going to take them and we're going to build a model in the computer, and that model will lose some of the precision, but it will give us useful information. So this is mathematical modeling. So we take a problem, we convert it into a mathematical discrete model, and then we can solve it using a computer program. So a computer program is an algorithm, and an algorithm is a sequence of very precise instructions. Right. So when we're dealing with discrete data, all the data is always well defined, so our instructions can also be very well defined. If you find this data here, then do this to this data over there, and so that's sort of an example of a statement in an algorithm. So discrete math provides us these tools that we can use to help us program, and they can help us determine the correctness of a solution to our discrete problem. They can help us determine whether or not our solution will terminate, so that's also a very important consideration. If we've done any programming at all at this point, chances are you've at some point written an infinite loop, so we want to make sure that that sort of thing doesn't happen in our solution. And the efficiency of the solution, of course. So in computer science, power is all about speed. So the more efficient your algorithm, the faster it'll run, and then the happier everybody is. So we're going to look at some example problems in discrete math and look at how we arrive at a solution. So these are sort of trivial problems, but they'll help to give you an idea of the sort of the math that we're dealing with, and the approaches that we're going to use to be solving them. So we visit an island with two types of inhabitants: knights who always tell the truth, and knaves who always lie. So it's possible this is an old riddle. So some of you may have heard it before, but we're going to go over it again, sort of using this discrete math model. And although you can probably think about it for a bit and come up with solutions to these problems, we want systematic solutions. So solutions that we can write as algorithms, and then so we can solve these using a computer, and then we don't have to think about them anymore. All right, so we have knights and knaves. So we visit the island and we're met by two inhabitants. We cannot tell them apart physically, but we want to get some useful information about them. So we know that they might be a knave, they might be a knight, and we know that the knights always tell the truth and the knaves always tell lies. So we meet two of them, and let's try and figure out who is a knight and who is a knave. So the man in green says the man in yellow is a knave, and the man in yellow says we are both knights. And so they've both made statements, and we want to take information from these statements in order to help determine the solution to our problem, which is which one is a knight and which one is a knave, or are they both knights or are they both knaves. So, all right. So first we need to model the problem. So what does it mean to tell the truth or tell a lie? So we all know, if somebody lies to you, they're giving you false information. If somebody tells you the truth, then they're giving you accurate information. But we want to boil it down even more specifically than that. So there's different types of statements that can be made. An imperative statement, so I can give a command. An interrogative statement, so I can ask a question. And a declarative statement, where I communicate information. And what type of information? Well, values. And since we are talking about discrete math, we want discrete values. So we want values that are definite and not sort of like, well, it looks sort of cloudy today. That's not really... We want stuff that we can classify as either a 0 or a 1 or a true or a false. So in this case, the information that we're interested in and the values can be classified as either true or false. So we have these two definite values that each statement can take. So in the context of this mathematical model that we just made, knights can only make declarative statements with a value of true, and knaves can only make declarative statements with a value of false. So this is how we've modeled our problem discretely. So the man in green says the man in yellow is a knave. The man in yellow says we are both knights. And each of these statements has a value of either true or false. And based on the value of those statements, we can determine the identity of the man in green and the man in yellow. So how do we solve this question, or others like it, systematically? So systematically means, as human beings, we sometimes have intuition about these sorts of things, but we don't want to do it intuitively. We want to build an algorithm that will solve it for us. Okay, so we want to solve this systematically. So we're going to look at what are the different possibilities. So there's only a finite number of them, since they can be either knights or knaves. That's two values. So each of them can take on either the two values. So if we list out all the possibilities, we'll find that there's four. We can either have that they are both knights, they are both knaves, or green is a knave and yellow is a knight, or green is a knight and yellow is a knave. Alright, so green is equal to the man in green and yellow is equal to the man in yellow. So we're going to sort of simplify our notation a little bit. So let's look at each case individually and see if we assign these values to these inhabitants of this island, given the statements that they made to us, let's see if these can be viable answers. So we're going to look at the first one, where they're both knights. So green is a knight, so we're going to assume that they're both knights, and then we're going to see what happens when we examine their statements in light of these ideas. So green is a knight, so green only makes true statements. And green says that the man in yellow is a knave. However, under our assumption, the man in yellow is a knight, and thus green gave us a statement that was false. Green lied to us. So this is what's called a contradiction. So we've assumed a set of values for our problem, and then we've worked through knowing what we already know to be true, and we found out that the values that we assumed cannot possibly be correct, because we've reached a contradiction, where on the one hand, we know that green must be telling the truth, but on the other hand, we know that green lied. So that's a contradiction. So the first case, where green is a knight and the yellow is a knight, cannot be true. So case 2, green is a knave and yellow is a knave. So both men are knaves, they both lie. So green is a knave and yellow is a knave. Both men are knaves. If green is a knave, then green only makes false statements. And green said the man in yellow is a knave. And the man in yellow is a knave. Thus, green actually made a true statement. So again, we reached a contradiction. If green is a knave, we know that green must only make false statements. However, under our assumptions that both men are knaves, green actually made a true statement. So that's a contradiction because it contradicts the things that we already know. Case 3. Green is a knave and yellow is a knight. So if yellow is a knight, yellow only makes true statements. And when we met yellow, yellow said, we are both knights. However, although yellow is a knight, green is a knave, thus yellow made a false statement. So again, we've reached a contradiction where our assumptions lead us to something that we know to be true, it should be false, or vice versa. So let's look at our fourth case now. Green is a knight and yellow is a knave. So if green is a knight, green only makes true statements. And green said the man in yellow is a knave, which is true. So far so good. If yellow is a knave, yellow only makes false statements. And yellow said, we are both knights. Well, green is a knight, but yellow is not, so we are both knights is false. But that's consistent with yellow's behavior. Yellow is a knave, so yellow is only going to give us false statements. So there's no contradictions. Thus, it can be true that green is a knight and yellow is a knave. It's possible. It could be one of many possibilities. However, in our case, we've already ruled out the other possibilities. So this is the only possible scenario that can be true. So the man in green is a knight and always tells the truth, and the man in yellow is a knave and always lies. So that's one example using, a very old riddle, and we can solve it systematically just by trying out all the different values and seeing which ones lead to inconsistencies. So it is possible we could have had a scenario like this where there could have been multiple sets of values for green being a knight and yellow being a knave, perhaps if we had a third inhabitant. So we could have had multiple possible true values. But in this case we only had one, so we could figure out precisely who was who in this case. So we can look at another variant of it. So we have a fork in the road and two guards. And these guards are clowns for some reason. So we know that one is a knight and one is a knave. So we have a little bit of information to start with. And they are guarding two paths. And one of the two paths leads to certain doom, and the other one leads to wherever we're trying to go. So we want to ask a single yes or no question and determine which of the paths is safe. So how are we going to do this, and what question should we ask? So now let's model the problem. All right. So again, we're going to ask a yes or no question. So yes, we're going to say is equal to their true value, and no is equal to our false value. So we want the truth value associated with our declarative statement. We're going to phrase it like a question. So we're going to provide a statement. We're going to phrase it like a question. Is this statement true? And we're going to pose that to these clowns. And then we know that if we pose it to one, they will actually tell the truth. They will give us the accurate value of the statement that we made. And if we pose to the other one, they're going to give us the not accurate statement. So they're going to give us the opposite value of the truth. All right, so hopefully that's clear. If not, perhaps it'll become clear in the next few steps. So we don't know, what we don't know though is which one is a knight and which one is a knave. So what is the question to ask? So we're going to be a little bit clever here. Right, so this is what I already described. We're making a declarative statement with a value and passing it through a clown that may change the value. So we're basically asking each clown, is this true? And if we ask the knight, the value does not change. So if our statement is statement X true, if X is true, then the knight is going to say yes. And if X is false, the knight will say no. And the knave will actually give the opposite answers, right? So if X is true, then the knave will say no. And if X is false, the knave will say yes. So what we want to do is somehow ask both of them. So we want to pass this information through both of these clowns, because if we know the behavior of each individual one, but we don't know which one to pick, if we can somehow pass our information through both of them, then we know what the end result is going to be. The value is going to change once. So would the other clown tell me that your path leads to safety and not certain doom? So this is our clever way of taking a statement and then asking it to one of the clowns in such a way that it filters through both of the clowns. So if the clown we ask says yes, then his path is the wrong path. That means his path leads to certain doom. So why is that? How does this question work? So if we ask the knight, we're really asking, would the knave say that your path is safe? Since the knave would lie, we would do the opposite. So the knight's going to tell the truth. So if we say, well, would the knave say that our path is safe, or that your path is safe? The knight is going to say no, he would not say that. So then we would take the path. If the path was, if the path was actually safe, then we know that the knave is going to lie. If we ask the knave, we're really asking, would the knight say that your path is safe? So the knight would tell the truth, but the knave is going to lie. So again, we would do the opposite. So we've designed a question that passes our value of our statement through both clowns, and only one of the two clowns changes the value in each case, no matter who we ask. So yeah, it's just a little bit clever. So these are classical puzzles that can be solved through a systematic process of elimination. So we haven't really done anything too clever, except, well, in the first case we considered every possibility. And in this case we designed a clever question such that the information would be filtered through both of the clowns. And since we don't know individually, we don't know which clown does which, but together we know if we passed information through both of them, then we know the result. So in that case, that's how that solution worked. So in these examples, only one of the possible solutions is accurate. In other words, it does not create a contradiction. And yeah, so here's a little cartoon that you might enjoy if you like XKCD. Right. Alright, so a final example problem that we'll look at, and this one is maybe grounded a little more in reality. So we've all been to traffic lights, and we've all seen how they work. And again, it's not that complicated a problem, but we want to illustrate these principles. So we're going to design a sort of a systematic way to solve this. So the problem is as follows. We want to decide on an efficient programming for the traffic lights. We want to write the schedule for which paths can have a green light at the same time. So we want to write a schedule for paths, which paths should have a green light at the same time, and then write a schedule, sort of an ordering to, when do we light up each green light. So observe that traffic lights have discrete values. So in a sense, this is sort of an easy problem to model, or easier. We're going to ignore yellow in this scenario. Yellow is just a precursor to red, so it doesn't make a problem logically. So we're going to model it into a discrete problem. So we're going to look at a collection of possible paths. So here we have a path from the intersection at A here to B. And so we're going to denote that AB. And we can also have AC. So we start at A and we end up at C. Notice that C, both of these, C is a one-way street. And so all the possible paths are listed by the, in order by the start, which street you start on and which street you end up on. So we have, AB, AC, AD. Now we have the one starting at B, BA, BC, BD. And we have the one starting at D, DA, DB, and DC. Nothing starts at C at this intersection because it's a one-way street that leads away from the traffic light. So we have all the possible values for A, starting at A, and starting at B, and then starting at D. So now our schedule, we have to take into consideration how we're going to schedule this. So what we want to do is we want to be able to green light paths at the same time that aren't in conflict with each other. So for instance, the path from A to B and the path from D to C can both be lit green at the same time, and there's no danger of them colliding. Whereas if we start at D and go to A and then go from A to B, those are in danger of colliding. So the two red lines that we can see here that are sort of following the paths that we're describing cross. Now that's a problem because, of course, if cars are following those lines at the same time, then there's a possibility of a collision. So it's a simple problem that we all are familiar with. This is not a simple problem. So how many possible schedules exist? There's actually more than you would think. So there are 9 paths that could each be green lit or red lit at any time in the schedule. 9 paths, and each of them can have either a green light or a red light. So each of them can take on 2 values. The same as before when we talked about true and false. So we can sort of have that same. It's a binary value. It can be either red or green. And given that there are 9 possibilities, 9 paths, and each of those paths can take on either a red value or a green value, each of them can take on any of 2 values. That means there are 2 to the 9 possibilities. Right, and that's. However, we're going to assume that it's never the case that every light is red. So then we're going to subtract 1. So there are 511 possible schedules. That's not even a schedule. That's just what should we green light at phase 1, let's say. So there's 511 options. So that's probably more than you would think. So what we're going to do is to solve this problem, this rather huge problem, is we're going to use something that we use a lot in discrete math, or math in general, and computer science in general. It's called a graph. So we're going to consider a diagram, and each of the possible paths has a symbol. So we see here, this represents the path from A to C, this represents the path from A to D, this represents the path from A to B. And we have B represented here. So we have, recall we had 3 paths from B, and we have 3 paths from D. So here we have all the possible. So basically there are 9 of these values, and these are the 9 different lights that can be either red or green. And now what we're going to do is we're going to connect any 2 paths that collide with each other. So if we look back up here, we saw that AB is colliding with DA. So if we go back to our graph, what was it again? AB and DA. So here we have AB, and here we have DA, and this edge between them represents the fact that they can collide with one another. Okay, so each of these edges represents a potential collision. So we cannot have a green light between AC and DA at the same time, right? And if we go back up to AC and DA, so if we go back up to here, AC is here and DA is here. So yes, that is a collision. All right, so that is how we build our graph here. And now we're going to assign colors to the symbols so that no pair of connected symbols has the same color. Now, don't confuse this with the light colors. This is, sorry, this is not the traffic light colors. We are referring to a coloring of the graph. Now, often these are done with numbers, but here We have red, green, and blue, not related to the traffic lights. But what we want is that if I color AB green, then anybody that AB is connected to must have a different color. So AB is connected to DB, which is red, DA, which is also red, BD, which is blue, and BC, which is blue. So everyone that AB is connected to has a different color. Now this color represents when we should green light the paths. And you'll notice that all the ones that are green are not connected to one another. So AB, AC, AD, and BA do not have edges between them, which means that they can all be green at the same time without danger of collisions, based on the way that we drew our graph, right? Based on each of these edges represents a collision, and since there's no edges between AB, AC, AD, and BA, then we can, there's no potential collisions there, even if we green light them all at the same time. So this is called the coloring of our graph. So we're going to get into, you don't have to remember this right now, but we will get into graphs later in the semester. So this is a coloring of our graph, and it actually not only tells us which paths we can green light at the same time without danger of collision, but it also gives us a schedule, right? So we can start with all the green paths, and we can green light those first. So we have AB, AC, AD, and BA are all green, and here we can see in the diagram all of them are represented, and none of them potentially collide with one another. So we can green light all of those at once. Next, we can green light the blue paths. There's only two of them, so there's BD, BC, and we can see that BD and BC won't collide with each other either. And finally, we can assign a green light to the red paths, and so DC, DB, and DA. And none of those are in danger of colliding with each other. So, and then that's the final green light. So we have, yeah. So we have, this is a three coloring of our graph. So we can do this light. We can schedule this light using only 3 different periods, 3 different phases where we green light different paths. So this is called the three coloring of our graph. And you may have noticed, if you haven't noticed yet, then you could point it out to you now, there are other possible colorings, right? So let me think here. So AD and BA, these can be, so AD could be red. And BA could be blue. And we still have a valid coloring of this graph. So this is not the only solution. There are other solutions, and you know, if you looked close enough, you could probably find more combinations. These are the 2 easiest ones because they each only have 1 edge. So BA and AD each only have 1 edge connecting them to another. So so they can take on either of 2 different colors. Okay. So these puzzles are simple instances of real-world problems. So we take a problem, we break it down into a mathematical discrete model, and then once we have a discrete model, it's often quite easy to translate that into a computer application that can solve it. So the solutions that we have discussed are applications of discrete mathematics. And yeah, one of the resources I'd like to point out to you here, it's as well on the Discord and on CU Learn, but the Discrete Math Study Center. So it's at these 2 web addresses, but if you go to one, you can find a link to the other. So that's hosted right here in the CG lab at Carleton, and it has lots of great resources. It has notes. They're terse notes. They're very they're short and to the point. They don't elaborate a lot, but it's a great place to review, and there's lots of good exercises as well. right? So that is our introduction to discrete math. Hopefully by now you have some idea of what discrete math is, why we use it in computer science, and a little slight idea of how we use it. So we're going to get into a lot more detail of how we use it a little bit later and in later years even. But for now, hopefully you have an idea of where we're starting from. And then the next lecture, we're going to start looking at, well, it's actually part of the same lecture, but we'll start looking at propositional logic, but it'll be a separate video. Okay, thank you.